All right, hello everyone. This is John again, and this is now part 2 on how to manually calculate a one sample t-test. So in the first video, the last video, I showed you how to manually calculate a one sample t-test by hand using a step-by-step process with provided example. In this video, part 2, we're going to continue with the same example and the same t-test results. The only difference this time is we're going to add a few more additional features to our results. We're going to add the confidence intervals, the effect size, and percentage of variance for our one sample t-test, but of course using the same example. And then the video after this will just be plugging in a one sample t-test into RStudio, showing how to calculate the t-test, confidence intervals, effect size, and percentage variance using the same example. The third video is just to give a demonstration on how the manual results would look when you're actually using R to calculate them. But let's continue. So as I was suggesting, the example question is the exact same. I'm going to quickly read it as the results that we calculated in the last video answer this question. So it says Bill finds out that the average student at his college campus walks approximately 7.05 kilometers a day, which is a population mean of 7.05. Bill buys a pedometer and measures how much he walks over the next 7 days. Bill finds out he walks approximately 9.07 kilometers a day, which is a mean of 9.07, with a standard deviation of 2 kilometers. Using Bill's data, calculate a one sample t-test two-tailed and determine if Bill walks more steps than the average student at his college campus. So, of course, these results were actually calculated in the last video, and they are as follows. Based on the results from our one sample t-test, we can reject the null hypothesis as Bill is walking significantly more than the average college student at his college campus. And here are the t-test results in scientific notation and are significant. So in this video now, we're going to continue with the same example question, but this time, based on Bill's results, we're going to calculate 95% confidence intervals, effect size, also known as Cohen's d, and percentage of variance, which is R squared, for the one sample t-test two-tailed. So the first thing we're going to do is calculate the confidence interval, and there's an actual confidence interval formula here. It is the sample mean plus or minus the t-value times the estimated standard error. These are all values that we actually calculated in the last video. All we're doing here is we're going to replicate these values to calculate what is the upper limit, or we're going to do the mean plus the t-value times this estimated standard error. And then we're going to do the same thing to calculate the lower limit, which is, instead of adding it, we're going to subtract the mean from the t-test times the estimated standard error. What is something that's important to mention here is that this t-value is not our actual t-value from the result. This t-value is actually coming from what is known as the critical region within the t-distribution table. So you can see here I have a table that I've copied and pasted from a textbook. These are available online, and if you're using a textbook, should be at the back of the book. What we're doing here is we're trying to find the t-value that rests at the two-tailed mark at 6 degrees of freedom, where p is going to equal 0.05. So here it says 2.447. That is our critical region and our critical cutoff, and we're going to use this value here in both formulas when calculating our confidence interval. Okay, so as it says here, we're going to repeat the formula twice, one for the lower, one for the upper, using the same means, the same t-values, and same estimated standard error, just adding or subtracting. That's the only difference. What I wanted to mention here and demonstrate very quickly is that confidence intervals can vary. Sometimes people calculate 50%, 80%, 95%, or 99%. This question was asking that we calculate the 95% confidence intervals, which gives us a t-value of 2.447. Here it is right in the table. But for any reason you decided to calculate different confidence intervals, let's say you wanted to be very conservative and use a 99% confidence interval, you would literally have to go within your table and find 0.01, because 0.01 minus 100 is 99%. So you could be 99% confident that as long as the result is above 3.7, you could be confident that you have a significant result. And that's what is going on here. So if you use 50% confidence intervals, we have to use our DF of 6. So 1 minus 0.5, so here's 50%, here's 80%, here's 95%, and here's 99%. I just wanted to highlight and color code just where you would be looking for different types of confidence intervals within the table, because each of these values here provides a different critical region depending on the confidence interval you choose to use. But we're going to go with the 2.447 as that's what was being asked within the table, within the question, sorry. One thing I'd actually like to mention really quickly is that the 99% confidence interval, which has a t-value of 3.7, if we look at our t-value from our question, which is 2.69, we can actually see it's no longer significant, and that's because it's just past the critical region at the 95% confidence mark. So here are the calculations on how to do the confidence interval. For the upper limit, where it's the mean plus the t-value at the critical region times the estimated standard error, we get 9.07, which is Bill's walking data, plus the critical region times the estimated standard error, which is something we actually calculated in the last video, to get an upper limit of 10.90. And then we can repeat the same thing below for the lower limit. We use Bill's walking data of 9.07 plus the t-value at the critical region times the estimated standard error to get a lower limit of 7.23. So based on a 95% confidence interval, so here's Bill's mean walking data, which is 9.07. We can be 95% confident that Bill walks anywhere as low as 7.23 kilometers a day to as high as 10.9 kilometers a day. So based on the results from Bill's data, calculate the 95% confidence interval. We already had these results from our previous video. Now we're just going to add the results for our confidence interval, like so. So at 95% confidence interval, we have our lower limit of 7.23 and our upper limit of 10.9. So now the next thing we want to calculate is Cohen's d, or the effect size. This is quite simple, and this is actually something you could have calculated right away pretty much without even having to calculate the one sample t-test, as all this information was actually provided within the question. We're just going to use Bill's mean data, subtract the population mean of walking data, which is 7.05, divided by the standard deviation, and that's the standard deviation for Bill's data. So using this simple formula, we actually subtract the two walking datas divided by 2, which is a standard deviation, and we get a Cohen's d effect size of 1.01. In order to interpret the effect size, there's usually tables that are provided to determine whether it's a small, medium, or large effect. These are usually within textbooks or online, and quite easy to access. And this one, which I took from a textbook, you could see that a d value, a Cohen's d, which is 0.8 or greater, really, is a large effect. So here we actually have a very large effect, and which just means is that Bill is actually walking quite a bit more than the average college student at his campus. If the effect was small, it would just suggest that he's not really walking that much more than the average college student, just maybe a bit more. But with such a large effect, we can be quite certain that Bill is walking quite a bit more than other students at the campus. And once again, with our question and the results from our question, we can just add the Cohen's d effect size to our giant scientific notation that is growing here. So we have our t-test, our confidence interval, and now our effect size, which is D equals 1.01. So the next thing we want to calculate is the percentage of variance, and this is usually known as a treatment effect. Technically, we didn't actually measure a treatment effect within this study or within this question. There's no treatment effect being measured, so this is probably something you wouldn't want to calculate for such a question. But if it asked you to calculate it, or let's say hypothetically there was a treatment effect, let's say Bill was put into a special type of walking program to see if it would endorse students to do more walking, then we could say there was a treatment effect, or that there was a treatment being used, and then we could use this formula. And this formula does require that you have already done certain calculations in order to use this formula. Here we actually need the t-statistic from Bill's data, which is over here in the table, 2.69, plus the degrees of freedom, which is 6. So to use this formula like so, we would do 2.69 squared divided by 2.69 squared plus 6, and we actually get an r squared of 0.54. And this is actually, once again, like Cohen's d, you would need to find a table, a percentage of variance table, in order to interpret how strong of an effect we have. And here the result is 0.546. Which is actually very strong, and you can see within the table anything above a 0.25 is quite a large effect, and we have doubled that. So hypothetically, let's say there was a treatment or an intervention program in place and Bill was a part of that intervention program, we could say that that intervention program in itself had a 54.6% impact on how much walking Bill was doing. And that's quite a bit. So that's really how you would use this result. And if you were to write it within your actual formula like so, you would include r squared equals 0.546. And that's literally all you would be adding based on the question as provided. So yeah, this video is a little bit shorter, but it just shows you how to manually calculate the confidence intervals, effect size, and percentage of variance for a one sample t-test. In the next video, video number 3, I'll show you how to do it in RStudio, pretty much using the same example and data set.